All right, hello class. Today in lecture 5, we're going to continue our construction of basic macroscopic thermodynamic principles from our underlying microscopic perspective. We'll review some of the highlights of the last lecture and kind of where we've come from, in which we've introduced a number of definitions that codify microscopic underpinnings of common thermodynamic quantities. We'll continue to build that structure up in this lecture. And we'll flesh out a little bit more what we've discovered in lecture 4, namely the microscopic perspective of the first law of thermodynamics. All right, so just to remind us of where we've come from, we, from our fundamental postulate, know how to describe the probability of observing a microstate. That restricts our attention to fairly artificial constructions, artificial systems, which are completely isolated. But we have from that identified a basic statement of systems in contact with heat baths. So for a system in contact with a bath, which is some big surroundings with which the system that we're interested in can exchange energy at some fixed temperature T, the probability of a microstate is proportional to this exponential function of the energy of that state. That constant proportionality will deserve a lot of attention. We'll get to that in some upcoming lectures, but it suffices to acknowledge where the information of the microstate resides, which is in this energy function here. We also introduced last lecture a generalization of a definition of the entropy due to Gibbs as a sum over microstates, the probability of that microstate times log of the probability of that microstate. That, as written, is a strictly negative quantity because the log of a number less than 1 is a negative number. So in order to keep entropy a positive number, we'll multiply it by negative, and to give it units, we'll use Boltzmann's constants. So this was from Gibbs. And that works whether or not we're in a system that is isolated or at fixed temperature, or quite generally in any other circumstance we can imagine. So these two are statements that work for systems in contact with baths at finite temperature. We, at this point, have a statement for the second law, though one that only holds in an isolated system. If we go back to an isolated system, a statement of the second law is that the change in the entropy in that isolated system, an isolated system is one in which the energy and all associated mechanical variables are fixed, is greater than or equal to 0 in a spontaneous process. So if we set the system up and it spontaneously changes, it must do so by increasing the entropy, provided that system is isolated. So taking us all the way back to where we started in this beaker experiment, where we imagine concentrating some ink at the top of our beaker and letting it spontaneously fill the glass, taking a volume of gas and putting it in the corner of some room and letting it spontaneously fill the room. Both of those are examples of processes that could be done in isolation has a definite directionality. The ink fills the glass and does not macroscopically reverse itself. The gas, if located all up in some corner of your room, spontaneously fills the room, is not likely to reverse. You don't spontaneously move all the gas particles back up into a corner. That would be unfortunate. You would not be able to breathe. So in a spontaneous process, the entropy increases. This was just a statement, microscopically, of a regression towards the mean, saying that if I start in an unlikely arrangement, having all the molecules co-located in some spot, the next observation of the system is likely to be one in which the system is in a much more probable arrangement, a much more likely microstate, a much more likely arrangement, and a much more likely collection of microstates. We do not, at this point, have a statement of the second law for a system that can exchange energy. That's something that we'll work towards today. All right, so those are 2 points that we should be feeling comfortable with. The last that I want to review is what we observed last lecture, which was a microscopic statement of the first law. Which was that changes in energy occur through 2 fundamentally different sorts of processes, those that we label those that we label heat and denote dQ, and those that we label work and denote dW. From our microscopic definition, our microscopic derivation of this law, we know that these 2 really are fundamentally different sorts of processes. The operative distinction is that work afford changes in the energy from processes that we control, while heat result in changes in the energy from processes we do not control. We can, as we've discussed and gave examples of, manipulate the size of a system, change its length or volume. We could add a pressure to do that, or physically change that size, and therefore do work on a system. We could change its number of particles and thereby do a sort of chemical work. What we cannot control is, as we do those processes, whether or not molecules happen to bump into the system we're manipulating, and therefore exchange energy, and thus potentially change the system's energy by heat, random fluctuations that we do not have our hands on. In any practical system, in any macroscopic system where we have an Avogadro's number of particles, this is something that definitely will happen and that we won't be able to avoid. Okay, so as I said, today we're going to continue building some structure of thermodynamics, how macroscopic systems change from these microscopic principles. And to do that, let's revisit in a slightly different way one specific sort of process that we can apply to the system, which is fairly straightforward to think our way through, a so-called adiabatic process. An adiabatic process is one in which there was no heat exchange. So dQ in an adiabatic process is strictly 0. An example of an adiabatic process, a more canonical example than we've introduced thus far, would be to imagine taking a gas in some piston. So imagine forming some volume in which the volume is wrapped in insulation, confines the gas to some scale, some size of a region, and manipulates that size through the application of a pressure. I could imagine moving that piston and compressing that gas by increasing the pressure. That gas is smushed up a little bit with some P prime greater than P. And in principle, if that system is wrapped in insulation, there's nowhere for the heat to flow out. If the gas is not able to transfer energy through the walls of the container, no heat flows. So this is a kind of canonical macroscopic example of an adiabatic process, at least one that can be done in principle. If no heat flows to the outside, then from the outside's perspective, from the surroundings perspective, nothing has changed, and thus there is no change in the surroundings entropy in an adiabatic process. It then follows that from the second law, which applies to some whole universe, some system plus surroundings, that the total change in the entropy, which in general has some component from the system and some component from the surroundings, in a spontaneous process, their sum has to be greater than or equal to 0. In an adiabatic process, the fact that the surroundings don't change would mean that we have a statement specific to the system for its direction of spontaneous change. Namely, in an adiabatic process, the system's entropy is greater than or equal to 0. Equal to 0 if there was no spontaneous change, if it was a reversible transformation. If it is a spontaneous change, that entropy change is necessarily positive. In what I've just outlined, compressing a cylinder, one should think about whether or not that was a reverse, whether or not that can be done reversibly, or if it's necessarily an irreversible process. what would be the conditions for reversibility in such an experiment. I don't have a lot of experience plunging gas cylinders. One could, and we've introduced this already, imagine doing a similar sort of thought experiment of an adiabatic process by bending a rubber sheet. Let's imagine bending it reversibly and adiabatically. We've argued that potentially one way of doing this would be to take this sheet in some vacuum or in some very dilute vapor, like the air around us does not conduct heat very well, applying some force to bend it, thus allowing us to go from some initially unbent state, denoted A, gradually increasing the force such that we afford a transformation. Ooh, that's a terribly bent sheet. It's a little bit better. Such that it now has some net curvature. This would be some state B. We'll explore the idea of reversibility a little bit more in the last half of this lecture. In this case, what do we really mean by reversible? What do we mean by applying a force gradually? Very specifically, we mean that we apply that force such that this is some external force that we are applying, such that it is always in mechanical equilibrium with the force that's restoring or opposing that bending. That sheet left by itself would want to be flat. I have to apply a force to bend it, which means that in general, if I apply a force, there's a force that is pushing in the opposite direction. If I apply a force gradually enough such that the system, the sheet, is always opposing that bending with a force that is equal and opposite in direction to the force I'm applying, that's what we would mean by a reversible transformation. Now to do this, to bend the sheet, I had to apply a force, so there is going to be some amount of work that was done. So that's some positive number. That there was no heat flow means dQ was 0. If dW is positive, that means that the energy of the system must have increased. EB is greater than EA, but it's reversible, so the entropy must not have changed. So again, I'll just highlight that a way to think about reversibility is that the system goes through a sequence of equilibrium states. I bend the sheet so gradually such that the molecules don't know that this macroscopic object that they are embedded in has changed. that the opposing force is always equal to the force that I am applying, which is the force that the system would generate irrespective of where it started from. So I could create this curvature through any number of transformations, and an equilibrium state doesn't care about how it's been prepared. So the force that is opposing it is independent of that preparation. This is what I would mean by a gradual reversible transformation. Now this process is to be contrasted with what I would have, or what would happen if I took my hands off of this sheet. If I set that external force instantaneously to 0, what I would see is that initially bent sheet with some finite amount of curvature is going to spring back flat. If there is no applied force, the work is 0. And this is something we can expect to happen spontaneously. If I took my hands off of this elastic sheet, it would do this spontaneously. It would flatten out spontaneously. So we expect this spontaneous process will have increased its entropy. SC would be greater than SB. But there's no work. We don't apply a force to cause this to happen. It's adiabatic. It's still floating around in some vacuum, which means that the energy of these two states has to be the same. So how could it be that the system changes, its entropy changes, and yet the energy is the same? Something to ponder. All right, that's an adiabatic process. We're talking a lot about forces as we apply external forces to the system to afford transformations of that system. We introduced a couple lectures ago a notion of a force, not as itself a mechanical definition, but through but in a definition in a way that meant that it was, that illustrated that it is something computable by counting. Namely, we introduced definitions of forces that were statistical in origin. And I think it's worth, as we continue this discussion of the first law and causing transformations of macroscopic states by applying external forces, that we consider a little bit further this definition that we've introduced thermodynamically for the internal forces, an internal force of a system. To remind you, we defined a force conjugate to a mechanical variable xi as how the entropy changes as I change that mechanical variable xi up to a factor of 1 over temperature. So we've defined a force through how the number of states, which is what entropy is, and how it changes as I change some mechanical variable. we should ask if this definition makes sense. Does it make sense to attribute the change in the entropy with change in mechanical variables to an actual force, something we imagine from Newtonian mechanics as having a very specific sort of meaning? It's something which is the generator of inertia in the system, causes acceleration. How is it possible then that it is related to just counting up a number of states? So let's flesh out that notion before we continue discussing consequences of the first law. So we have, from Boltzmann, observed that the entropy is just the number of microstates in an isolated system. So it is a function of those variables that we set in our isolated system that are conserved. It is a function of the energy of that system and that set of mechanical variables. Which means that if I ask for differential changes in the entropy, a change in the entropy can occur through changes to the energy, holding those mechanical variables fixed, or changes to those mechanical variables holding the energy and the other variables fixed. Those are the two ways that I can affect changes of the entropy, differential changes of the entropy, either by changing the energy of the system or changing the mechanical variables. dsdE has an operational meaning. It is what we mean by 1 over the temperature. ds dx is what we've claimed to be equal to minus this mechanical force divided by temperature. So is this a force like we would imagine the Coulombic attraction between different charges being a force? Does this have the same sort of mechanical meaning as a force would typically, as we'd imagine a force typically does? One note of caution, let's write this in red. This sort of differential relationship for the entropy that we've just written down is true for equilibrium states. Indeed, our definition or our derivation of the first law imagined that the probability distribution for a microstate was given by that Boltzmann form. These sorts of then differential relationships require that we're moving between equilibrium states. This is a simplification that allows us to compute delta S by simply integrating over these differential changes in the entropy. But this is only true for a reversible process where we go through equilibrium states. So as long as we're restricting ourselves to equilibrium states, we can compute changes in the entropy from these sorts of thermodynamic-like relationships. All right, so constraining ourselves to such cases, then for an infinitesimal, reversible, and adiabatic change, so adiabatic means that the change in the entropy is just due to changes in the system. Reversible, however, would suggest that there is no change in the entropy. So ds must be 0. ds, as we've just written, is nothing but 1 over t dE plus what we would say from up top is how the entropy changes with a mechanical variable times the change in that mechanical variable. This is what we've claimed is related to a force. Let's see if that's true. So if we have a reversible adiabatic change, total change in the entropy is 0, which means that there's going to be a relationship between changes in the energy and these changes in the entropy due to changes in the mechanical variables. If we remind ourselves that the first law tells us that changes in the energy are afforded from how the entropy changes with energy. Sorry, there's no change in the entropy due to changes in the energy. Let's see, so we have minus T ds dx. All right, one more time. So if we just rearrange the top line, we must have that dE is equal to minus T times the sum over all the potential ways the entropy can change due to changing mechanical variables. That's just rearranging the line above it. But dE from the first law is also how the work is accumulated plus how the heat is accumulated. This adiabatic change means that there is no heat. So it must be then that dW, reversible in this adiabatic process, is equal to minus T sum over ds dxi times differential changes in xi. So the work is some constant related to changes in entropy with changes in mechanical variables times dx. Indeed, if we plug in our definition that we've claimed that ds dx is nothing but minus f over t, we indeed have just found that the work is nothing but f dotted into dx. Some set of external forces, which reversibly are always equal to in magnitude, to the internal forces. Indeed, in an adiabatic process, this definition of a force really corresponds to a mechanical operation. It tells you how we can do work on the system. So in an equilibrium system, there's an intrinsic relationship between mechanical quantities, forces, and statistical quantities, like the number of microstates a system can arrange itself in, given some constraints. This is not true away from equilibrium. There are not simple relationships between mechanical and thermodynamic quantities, but in equilibrium, this is true. So indeed, we would say that ds dxi, with the right things held fixed, is up to a factor of t, a force. Which then lets us write down the first law really convincingly now as changes in the energy being due to TDS, a heat term, how the energy changes through changes of the probabilities of states as represented by the entropy, plus a work term, something fundamentally mechanical, and yet something we can also compute by counting. Rearranging this gives us a differential change of the entropy in terms of 1 over T dE minus F over T dx. All right, so that's a discussion of statistical forces. Let's use this more robust understanding to now construct statements of spontaneous processes. In the more typical case we confront experimentally, one in which heat can flow. So let's ask the question, what determines spontaneity when heat can flow? Or alternatively, what is a statement of a spontaneous process in a system that can exchange heat with its surroundings, so an open system, not an isolated system? Well, to do this, we have a construction that we've found useful before. Let's imagine embedding our system in a larger surroundings, one in which we have wrapped an insulation, held rigid and impermeable, so it itself constitutes an isolated system. For good measure, it's really wrapped in insulation. Let's pick out part of that box to call our system. The remaining we call a bath, and imagine that the way the system and the bath interact is by exchanging energy. So everything in that brown box obeys a statement of the second law, which is that the total entropy must increase in a spontaneous process. Which is decomposable into a change of the system and a change of the surroundings, the bath. Let's imagine that the mechanical variables of the surroundings are fixed. We're only performing manipulations on the system. That means that any change in the energy of the surroundings is not accompanying changes due to work, but are all are all being affected due to changes in heat. That is to say that as we manipulate the system, the things in this little box, the system and bath can interact through exchanging energy. We'll manipulate the system by manipulating its mechanical variables, which means that the only way the surroundings change is through the heat released from the system into the bath. Let's assert that, like before, the bath is really big. If the bath is really big, changes to the system are done while the bath stays at equilibrium. If the bath is at equilibrium, the processes are reversible. We can compute the heat by this reversible limit, whereby it's just nothing but the temperature times the change in the entropy of the surroundings. Now note, the heat in general is not an exact differential. It is computable from knowledge of an explicit path that I manipulate the system through, but in the limit that the process is reversible, it can be computed just by the endpoints, just by an exact differential. And if the bath is really big, any manipulation to the system doesn't move the bath far from its equilibrium state. So processes done in the system have, we assume, only reversible effects to the bath, in which case we can compute the heat transferred by noting its change in entropy. If that is true, a restatement of the second law as the total change in the entropy being positive is to note that the change in the system plus the change in the heat of the surroundings over the temperature is greater than or equal to 0. Substituting the entropy change by its reversible limit, where it is nothing other than the heat. Now, if the bath gains some heat, it must be because the system released it, or that is to say that heat flows to the surroundings are, equal and opposite heat flows from the system. Noting that equality, we can rearrange this above statement to changes in the entropy of the system necessarily being greater than or equal to changes of the heat in the system divided by the temperature of the bath, where the temperature of the bath is a constant because its changes are reversible. So now we have arrived at a statement that just has system information in it. It says that a consequence of the second law in terms of a system that can exchange energy with its surroundings is that the corresponding change in the entropy of the system has to be greater than or equal to the heat released by the system divided by the temperature of the bath into which it releases that heat. So this is a statement then of the second law. The likelihood of a spontaneous change in an open system, a system that can exchange energy with its surroundings. This statement of the second law is known as the Clausius inequality. It actually was the first to be written down in mathematical form. Okay, what are the implications of this formulation of the second law? Let's understand that by considering a process involving the same heat bath and comparing different initial and final states. So let's compare processes which occur in the same large heat bath at some temperature T, and excuse me, the same initial and final states. Let's go back to that polymer pulling example. So let's imagine taking our glass beads with a polymer tethered between them at some initial state with corresponding energy E1. Let's imagine pulling that polymer apart either reversibly to some final length or irreversibly, so at some finite speed, but to the same elongation length. Oh, I can do better than that. We've seen examples of what happens when you pull it really fast. Most of the polymer has not had time to react and thus stays balled up over on the left. So let's call this E final. And let's actually call that E initial. All right, so what are the implications of the statement of the second law due to Clausius in such a case? Well, dE for this process, as always being a sum of dW and dQ. In the reversible limit and in the irreversible limit, the sum of the heat and work have to be the same because I end in the same point. EF minus EI is the same. So if this is the irreversible dW and dQ, heat and work, and this is the reversible heat and work, the sum of the heats and works have to be the same because I start and end in the same position. Now in the reversible limit, we can compute that heat by noting the temperature of the bath and computing the change in the entropy. In the reversible limit, differential changes in the entropy are exactly equal to the heat released. Rearranging this equality, we have that the work done irreversibly is equal to the work done reversibly plus the heat reversibly, which I can compute from T ds, less that the heat released irreversibly. Now this quantity is precisely what Clausius said was greater than or equal to 0. If that is necessarily greater than or equal to 0, it must then be the case that the work done irreversibly is necessarily greater than or equal to the work done reversibly. Let's try that again, box it up, that's a nice result. So a reversible process requires at least the amount of work at fixed t as any process that does some work on the system requires at least the reversible amount for a transformation. Let's give me a little more room here, move that down and make that note. Another way to say that is a reversible process is that process which requires the least amount of work for a given transformation at fixed temperature. Indeed, we saw that in the simulations. If we pulled that polymer very quickly, more often than not, and with very high probability with a large chain, the work done over the course of that protocol was much, much larger than if we did that same, afforded that same transformation, but did the pulling very slowly. So if we work in the reversible limit, that is the minimum amount of work required for a transformation. In the irreversibility, in the finite time process, then necessarily has greater than or equal to the work required reversibly. We can make this a little bit more precise by actually thinking through that pulling experiment a little more quantitatively by noting relationships between the force that that polymer opposes pulling with. So again, let's imagine our beads with a polymer tethered in between them. And that one on the right is what we grab onto and pull by applying some force. Let's imagine that that force is some force external and its magnitude is equal in a reversible limit to the force that opposes that pulling, the force, the intermolecular force between the ends of the polymer. Now, for a simple model of a polymer, it is known that the internal forces of that polymer are proportional to their extension with a constant of proportionality we'll call alpha that depends on the temperature. but does not depend on the length. Namely, that is to say that polymers tend to act like simple Hookean springs. Their forces grow in proportion to their displacements. In such a system, the work can be computed from F times dl, and the work done by an external force, therefore, is that external force integrated over whatever elongation I'm prescribing by my protocol. The reversible work, so that is general, the reversible limit, therefore, is given by an integral over dl times those internal forces of the system, which, as we've just noted, are themselves a function of L. Now, the reversible limit is when you have this mechanical equilibrium. The forces opposing the external forces are equal, and thus I can replace the external force I'm applying in my calculation of the work with the internal forces that are equal and opposite to it. Okay, well, let's think about this experiment then in a reversible limit. I can do that by plotting F versus L. And let's imagine pulling that polymer between some length L1 and some larger length L2. Now, in the reversible limit, we have a relationship between the force and the length, which is a line with slope alpha. A name for such a relationship between internal forces and mechanical variables is an equation of state. For an ideal gas, one would say the equation of state is the ideal gas law relating the pressure to the volume and the temperature. All right, now let's imagine I ask for the work for a reversible process going between L1 and L2. That would mean that at each extension, I'm moving along this equation of state line. So I take the system initially at L1, I apply a force which increases with length into L2. The reversible work, therefore, is the integral under that, the integral of F dl between L1 and L2, which graphically is then just the area under this curve. If I give you that constant A of t, you can then compute that area explicitly. So that's the reversible work to go between L1 and L2. We can imagine other sorts of processes that afford the same change in length. Well, a different way of going between L1 and L2 would maybe be to apply a constant force. What are the implications on the work in such case? Well, again, if I plot my equation of state, which is nothing but this line going between L1 and L2. Well, if I start in L1, let's imagine applying a constant force of size F external going between L1 and L2. In this process, relative to the reversible process by which we stay on that equation of state line, we would note that this constant force experiment clearly requires more work. You can note that by noting the areas under the curve. The area under the reversible curve up here is smaller than the area under this curve. So indeed, this statement of we've derived from the Clausius statement of the second law that the work required for a transformation is necessarily greater than or equal to the reversible work, at least in this example, seems to hold true. This example would require more work than the reversible limit. Okay, well, some of you are clever. You might be saying, well, hold up. What if I apply a different constant force? I can imagine choosing an external force say one down here. What if I chose that external force? So I would start at L1, I would apply that constant force to try to bring myself to L2. That's a non-reversible process, an irreversible process, but one which certainly has a smaller area under the curve. Is that something that we could actually do? Could we apply this smaller force? What do you say? Is this possible? This would seemingly violate Clausius' statement, or the statement we derived from the Clausius statement. What's wrong with it? Indeed, if I applied only this size force all the way at L2, remember, this line is the force that the polymer pulls back on, or pulls back with. If at L2, the force the polymer opposes external forces with is that large, I'm not applying a large enough force to counterbalance it. I'm not going to get all the way to L2. The force opposing the external force is larger, so I won't affect that elongation of the polymer to begin with. It won't go anywhere. So indeed, these sorts of things don't seem likely. And in fact, Clausius would say, are impossible. It's not likely to be able to apply small forces and recover or do work, to affect a change in the system with smaller than the reversible amount of work. That Clausius would say it would be against the law. But I'll bunch. All right, very good. Let's keep going. Let's understand an additional implication of the Clausius statement. Another way to say the Clausius statement that ds is greater than or equal to dq by t. Again, these are statements of the system in contact with a bath at temperature T, is to remind ourselves, well, we could always rearrange dq to be dE minus dW. That's another way of stating then the second law due to Clausius. Rearranging this would say that dW is greater than or equal to dE minus T ds. All right, that's a manipulation, sure. If we note that the temperature is fixed, we can rewrite this differential change dW as being greater than or equal to the differential of E minus Ts. Again, temperature fixed, so if I apply that differential, T is constant, I get differential changes just due to S. So the work is necessarily greater than or equal to changes of some quantity, E minus Ts. Does that look familiar to anybody? You know, that's an old friend, right? Who remembers what you call thermodynamically what you get when you take the energy and subtract off T times S, temperature times the entropy? We will use the symbol A as equaling E minus Ts, and that, of course, is nothing but the so-called Helmholtz free energy. Why do we define such a quantity? Well, if no work is done on the system, that means that dW is 0. The second law then becomes, again, up here, it's what we then define as A. We would say that delta A at fixed temperature, which we use to define this inequality, and mechanical variables, which have to be fixed in order to not do work on the system, that must be less than or equal to 0 for a spontaneous process. Now at fixed T and X. So indeed, a natural quantity arises that tells us about the direction of spontaneous change in cases where a system is in contact with a bath at a fixed temperature. In such cases, the quantity, the Helmholtz free energy, is something that necessarily decreases in a spontaneous process. Therefore, just like in an isolated system, equilibrium is that which maximizes the entropy, where differential changes are 0, the equilibrium partitioning under conditions of fixed temperature will thus minimize A. Why would we call this free energy? Where does that nomenclature come from? From back up here, the E quality is associated with a reversible limit. So in the reversible limit, the work is equal to the change in the Helmholtz free energy at fixed temperature. So the Helmholtz free energy tells us about the work that is extractable for free, the amount of the possible amount of energy that can be extracted in the form of work. Okay, so we've just now introduced another old thermodynamic friend, the so-called Helmholtz free energy. We've really begun building up the whole formalism of thermodynamics from these microscopic principles. It's worthwhile taking a little detour that we'll start here in the last 10 minutes of class and continue on next lecture to talk a little bit about the mathematics of thermodynamics, to talk a little bit about some of the principles behind the functions that we'll be manipulating really throughout the rest of the class. So let's begin that detour. Okay, we're going to introduce some language. For example, A, the Helmholtz free energy, is what we would call a natural function of T and whatever set of mechanical variables we're interested in. What we mean by natural function is that differential changes in the Helmholtz free energy, defined as differential changes in E minus Ts, in general, if all of those quantities can change, will be equal to dE minus T ds minus S dt. In a reversible system, dE is nothing but T ds plus F dx. That's dE, copying down the rest, minus S dt minus T ds. What we're left with, this cancel, is minus S dt plus F dx. So a natural function is a natural function of two variables a natural function of some specific variables. What that means is that changes of that original function occur through changes of those variables. To say that the Helmholtz free energy is a natural function of temperature and the mechanical variables would be to say that differential changes in the Helmholtz free energy are affected by differential changes in the temperature and the mechanical variables. Now, in many cases, in chemistry, in the context of chemical systems, the two major ways that we will mechanically manipulate the system are through PV work and chemical work. So a useful way of writing down the Helmholtz free energy in such instances would be to define those works explicitly and say that changes in the Helmholtz free energy dA are equal to minus S dt minus P dV, a work term by change in the volume, plus mu dN, the chemical work term for changing the number of particles in the system. That then gives rise to other relationships, other definitions for the quantities S, P, and mu. This would mean that changes in the Helmholtz free energy with changes in the temperature, if I fix the volume and the number of particles, is what I mean by minus the entropy. If I fix V, this term goes away. If I fix N, this term goes away. If I divide through by dt, and thus I'm asking how the Helmholtz free energy changes with temperature, that's nothing but the entropy. Analogously, changes in the Helmholtz free energy from changes in the volume at fixed temperature and number of particles is what I mean by minus the pressure, and so on. To reinforce this idea of naturalness, A being a natural function of T in the mechanical variables, we could note that in principle we could write A as a function of entropy, volume, and number of particles, rather than temperature, volume, and number of particles. We can write out a function however we want. If we did that, we would have dA. If it's a function of S, V, and E, that means its changes occur through changes in entropy, changes in volume, and changes of number of particles. Changes in the Helmholtz free energy through changes in the entropy occur through ds dA and fixed V and N. Changes due to the volume through dA dV at fixed S and N, and due to the number by dA dN at fixed S and V. Now, while S is simply related to dA dt, how the Helmholtz free energy changes with entropy is not so simple. It's not got a simple definition in the way that we would find if we wrote the Helmholtz free energy down in its natural variables. So that's one little bit of the mathematical structure of thermodynamics. A last little bit to note is to look back we could have said that the energy, which in the reversible limit is TdS plus F dx, is therefore a natural function of S and X. So what would it mean if I ask for differential changes in the energy at fixed S and X? What does that correspond to? In going from the energy to the Helmholtz free energy, we've essentially exchanged the roles that S and T play. While the Helmholtz free energy has these F dx terms, like up here, TA is F dx minus S dt. The energy, well, it has those mechanical variable terms F dx, but the roles of S and T have swapped. What was a differential in S became a differential in T. So what is the mathematical relationship, mathematical structure underpinning that swap? We defined A, the Helmholtz free energy, as E minus Ts. That T and S are what we'll call conjugate pairs. What that means is that the energy, which is some natural function of the entropy, it is differential changes in the energy occur through differential changes in the entropy. The A can be thought of as the function E of S less that S times how energy changes with entropy at fixed mechanical variables. dE ds at fixed mechanical variables from up here, the differential equation for the energy, is the temperature. So this equation we've written down, this definition for the Helmholtz free energy, has some structure. It took a function, the energy, and subtracted off a variable it is a natural function of, the entropy, times how that function, the energy, changes with that natural variable, the entropy. This formulation, this defining a function in this specific way, is a mathematical operation that has a name. Does anyone know what that name is? It's known as a Legendre transform. As long as that original function E is convex, this transformation is invertible. What does that mean? It means that if I gave you the function E of S, you could, through this definition, construct the Helmholtz free energy. Invertibility means that if I gave you the function, the Helmholtz free energy, you could then reconstruct the function of the energy. And those functions, the original function of the energy and that inverted from the Helmholtz free energy, would be identical. Another way to say that is that this is a transformation which, in the limit that E is a convex function, is unique. It doesn't lose any information. The information contained in E of S is identical to the information contained in A. That means that whether or not we use E or use A to describe our system is therefore a matter of convenience. If they contain the same information, whatever makes our life easier is what we should use. And indeed, this is exactly why the Helmholtz free energy is introduced to begin with. The energy is something, because it's a natural function of the entropy, which is a little cumbersome to work through, to use, because we don't manipulate the entropy directly in most experiments, while a natural function of the temperature has great benefit. That's something we can affect changes in straightforwardly. Because they contain the same information, we can always back out information about that original isolated system. Okay, well, that's all I got for this week. I'll look forward to our live session on Thursday and any questions you have on this lecture then. All right.